Welcome to the lecture on technology of melting. So, in this lecture we will discuss about the practices which are followed in melting. Normally we will confine our studies to cupola melting and in the arc furnace or induction furnace. Then also we will discuss about the refractories which are used in the furnace. So, in the terms of lining, so about them also we will discuss in brief. So, let us come to the cupola operation. So, we had earlier studied in the previous class that cupola is normally used for melting iron, mostly cast iron, and it is normally nowadays replaced with the arc or induction furnaces, but still they are used for medium or small scale foundries, because it is a cheap operation based process. So, as we know that in the cupola operation you have these activities which are to be followed. So, first is preparation of cupola. So, in that basically you are keeping the cupola prepared by cleaning, by putting the things in place. So, once you have the coke bed prepared at the bottom, then you have the alternate layers of metal or ore, then coke and then flux. So, that alternate layers are kept in. You have the tuyers ready, so that you can start putting the air into it, blasting it. Then the next operation is firing the cupola. So, firing the cupola means, certainly when we talk initially we preparation of cupola means you are keeping the cupola clean and neat, so that you can start the operation, keep the coke beds ready. Then you are igniting this by firing it. So, you can use the kindles of wood to fire from the bottom, and then you fire the coke bed with air passing through that. So, once it is ignited, then you are charging the cupola with that charged metal, that is metal, coke and limestone alternate layers, and then the soaking of iron takes place. So, that iron will be melted and then it will start coming out, temperature will go on increasing and it will be melting, coming down, air blast is opened. So, then once this air blast is opened in the later stages, it increases the temperature of the molten metal which is coming through the coke bed and trickling down into the bottom portion of the cupola, and then you are pouring the molten metal. So, this is how the process goes on in cupola. You have to adjust the composition of the charge, you have to adjust the composition of various elements, so that if suppose there is deficiency of certain alloying element, you will have to add them and you have to make it as per your requirement. Now, coming to the point of air requirement in cupola. So, basically you need to have the air which is to be blasted for the combustion of the coke. So, this air requirement is there, and that is normally some value. So, on the basis of that you can find. So, if you have a certain amount of metal, in that case you need to provide some amount of air at certain pressure. So, you have basically for a charge, the charge is the molten metal which you get, it is by melting the iron ore or the scrap which you put in that, then it is combining with the coke and the limestone, that basically that works as the flux. So, that will form the slag. So, air requirement is normally 8.4 cubic meter of air per kg of coke. So, if you know the amount of coke which is required to burn, then you can find the amount of air which is required. Now, the amount of coke basically depends upon what is the amount of molten metal to be melted, or metal to, there is a metal to coke ratio. So, there is metal to coke ratio, that is also known as coke rate, and that basically varies from 6:1 to 12:1. So, if you have 6 kg of metal, then you need 1 kg of coke, so that it can be melted and then you can get the liquid metal. Now, the thing is, there is one more understanding and one more calculation which is given, that the plan area, that is 14 centimeter square of plan area of the cupola is required for delivering 1 kg of metal per hour. So, if you want the metal delivery rate at 1 kg per hour, normally you need 14 centimeter square of the plan area, that is of cupola. So, these are the formulas which are normally used for calculating the dimension of the cupola, the amount of coke, and once you know the amount of coke, you can find the amount of air requirement. So, suppose for example, if you have the plan to have a 5 ton per hour of metal requirement, and in that case, if you take the metal to coke ratio, if the ratio metal to coke is taken as 8:1. So, in that case, for 5 ton of the per hour of the metal to be delivered, you need amount of coke per hour, that will be 625 kg. So, that is 5000 kg upon 8. So, that is 625 kg. Now, this was basically for 1 kg per hour of the coke requirement. So, for 1 kg, it is, this is the plan area required for the cupola. So, for this, for 625 kg coke, plan area required of cupola, that will be able to deliver you this amount of 5 ton of metal per hour. This will be 625 into 14. So, this is 8750, that is centimeter square. And once you know this 8750 centimeter square is basically the area of the cupola, that is its cross sectional area. So, you can find the diameter of cupola, and diameter of cupola can be found out. So, that is pi by 4, d square will be 8750. So, d will be under root 8750 into 4 divided by pi. So, once you get that, you can calculate what will be that. So, 8750 upon 3.14 into 4 and under root. So, it is something close to 106 centimeter. So, you can have a cupola of diameter basically. So, this cupola diameter has to be something 106 centimeter. So, the cupola diameter, so you have the cupola here. So, this diameter has to be 106 centimeter, which will provide the metal delivery rate at a value of 5 ton per hour. So, this is how you try to find out the dimension of the cupola, amount of coke required. Based on the amount of coke required, you can have the requirement of the air. Loss and gain of alloying elements during melting. Now, during the operation of cupola melting, there is loss or gain of many alloying elements. Now, among these alloying elements, normally we have carbon, silicon, manganese, sulfur and phosphorus, and then rest is that is iron. Now, we will discuss about the basically loss or gain of alloying elements during the melting process, and we will discuss mostly about the elements, that is carbon, silicon, manganese, phosphorus, sulfur and iron. So, basically what happens, the carbon basically once the molten metal comes down, then this basically picks up the carbon from the coke. So, it has basically reaction with the, so it has basically it is in contact with the coke, because we are putting the alternate layers of coke. So, it is in contact with that coke. So, it picks up the carbon from there, then further it comes through the coke bed. So, there will be pickup of carbon. So, some amount of carbon is picked up, maybe 0.1 to 0.23% or 0.3% maximum, that much pickup is there of carbon. So, you have to adjust the carbon composition by putting proper amount of carbon in the charge itself, and then there will be some pickup during the melting process. Now, that pickup will depend upon the quality of coke, the size of the coke, also the amount of coke, the coke bed height, all these things will basically decide about the carbon pickup. Then coming to silicon. So, silicon is basically lost during the process. So, there will be loss of 10 to 15% of silicon when the melt comes down, and when there is combustion process, during that process the silicon is lost, and this silicon has to be basically balanced. You have to provide extra silicon to have the composition within limit. So, that can basically either be compensated by providing the charge in such a way that you have silicon in the charge, or so high silicon content charge may be given, or you may do the addition of ferrosilicon, which has the silicon content to a quite larger extent. So, that will compensate for the loss of the silicon. Similarly, manganese. So, manganese also is lost. There will be loss of manganese, and this manganese has to be basically compensated again by the addition of ferromanganese. So, these are the elements which are lost. Now, is sulfur. Now, sulfur is basically there is a pickup of sulfur. So, because the coke which we use, it has sulfur. So, the melt picks up this sulfur, and that is why you will have to see that what kind of charge you have to provide, so that there should not be much of the sulfur. So, it will depend upon the type of coke you provide. If the coke has larger amount of sulfur, there will be larger pickup of the sulphur, and large amount of sulphur is not basically good for the castings, especially for the production of SG iron castings or ductile iron castings. This presence of sulphur is deleterious for the nodularization process. So, you will have to see that the sulphur content is not picked up. So, basically even you can go for proper basic lining, so that the sulphur pickup is inhibited. Then phosphorus basically there is not much of the change in the amount of phosphorus during this cupola melting, and then there is rest of iron. So, iron is also lost in the process, and something close to 0.3 to 0.4% of iron is lost during that. So, you have to balance it by putting the charge which is rich in iron. So, this way you are basically balancing the, or you are maintaining the proper composition of the charged metal. Then comes factor affecting the efficiency of cupola. The factors which are basically affecting the efficiency of cupola are basically coke rate, blast rate, coke size. So, these are basically affecting the quality or the efficiency of cupola. So, as we know, this coke rate has to be basically proper, so that the cupola melting is proper. Similarly, you have the blast rate. So, blast rate is something that how much of air is required to be put into the cupola, and that is normally 70 to 125 centimeter cube of air that is required to be sent, and that is for per square meter of cupola area. So, this is the blast rate which has to be maintained. Now, next is coke size. So, coke size also, there are two coke sizes. One is for the coke which is in the charge which is given, another is the size of the coke in the coke bed, and basically so coke has to be used in the coke used along with charge and in the coke bed, and coke used in coke bed. So, basically it will vary from 50 to 75, and this will vary from 125 to 150. So, normally this size is varying from 50 to 75, basically this mm, and this 125 to 150 mm of the size of that coke, that is diameter of the coke normally is used. So, depending upon what is the diameter of this cupola, that is the plan area, based on that you are normally going for these sizes of the coke. So, these are the factors which affect the efficiency of the cupola. Now, there are many developments in cupola melting, and we had discussed about few, that is hot blast operation, where we increase the temperature of the air and that increases the metal delivery rate. You have water cooled cupolas, where what happens basically in many cases there is large amount of corrosion or there is erosion of the refractories, and because of higher temperature and because of the reactivity of the slag. So, that in those cases or when the temperature is quite high, what you do is you may provide the water jackets on the side of the cupola, or even we can spray the water. So, that is continuously done, so that so in that case basically you have to increase the temperature, so that the drop in temperature is compensated. So, this is also practiced. So, wherever you do that water cooling, you do not provide the refractory lining. So, this way you are increasing the efficiency of the cupola. Application of basic lining, many a times you need to have the basic refractory lining to be provided, because for the efficient removal of the sulfur and phosphorus, this basic lining is to be provided. Acid slags are not effective in that case. So, you provide the basic lining. Oxygen enrichment of the blast is done, and oxygen enrichment of the blast basically increases the metal temperature. So, that increases the efficiency of the cupola. Calcium carbide is also used as a flux, but its main purpose also is to go for the reaction, and that reaction is exothermic reaction. So, large amount of heat is generated, and that increases the temperature of the melt. So, your good quality of melt you are getting at higher temperature. Then varieties are cokeless cupola, which we discussed, that is basically where the coke is not used, you use the ceramic refractory beds. Use of sponge iron is also reported in the charts. So, that basically this is helpful in the sense that, so in this case your slag which is formed, that is more less viscous. So, that way it is becoming easier to take the slag out. Then you also use the fluxes, primary and secondary fluxes, primary in larger quantities and this in smaller quantities. You have different kinds of fluxes which are used in the cupola. So, that you have, we know that you have different kinds of fluxes which are used in the cupola. Primary fluxes you have dolomite, magnesite. In the secondary fluxes you have fluorspar. All these fluxes are used, and you have about 5 to 7% of fluxes are normally used, and that is of the weight of the metal charge. So, this way you use the different kinds of fluxes. Then we will come to the requirement of the practice of melting in case of electric arc furnace. So, in the electric arc furnace, as we know, there is a typical electric arc furnace known as Heroult furnace. Now, in the electric arc furnace, normally you can go for up to maybe 5 to 125 tons of casting. So, you can have or even a smaller value, even from 1 ton onwards to 125 tons of metal can be melted in one go in these electric arc furnaces. Now, in these cases you have the diameter ranging from 2 to suppose 5 meters, that, and for a typical 10 ton of metal, for 10 ton metal you have diameter of 3 meter, 2.5 meter of height, and then you have basically a 25 mm thickness of solid cell which is around that, and the refractory thickness is quite big. So, this way you have some outer dia and inner dia of the furnace, and in between you have the refractory cell. So, that is maybe of the order of 30 to 40 mm or 50 mm. Now, what happens in this case, the charging practices. So, as we know, in the case of electric arc furnaces you have electrodes from the top which are lowered, and once they come in contact with the charged metal, then the arc is developed, and this arc is basically able to melt the metal. Now, the practice is that during the melting practice it is to be kept in mind that the arc should not be in a position to basically do the damage to the lining. So, your charged material should be properly kept and charge should be, so charge is basically normally heavy scrap. So, that comes about the runners or risers heads, then you have medium scrap and light scrap, medium scrap and light scrap. So, what happens, it is properly distributed in the furnace, so that the requirement is that it should properly be melted and it should not be in a position to damage the lining, because the arc, if it goes and if it hits the furnace refractory, that refractory may get damaged and that may be eroded. So, that is seen that how you are putting the, so normally it is seen that just below the arc, where the arc is initiated, closer to that the heavy scrap should be there, towards the end you must have the lighter scraps. So, and then, so once it is melted, the arc is basically prevented to completely directly strike the bottom and damage the lining. Now, in this case what we do is, you have acid line or basic line, basic lining. So, that is done depending upon the type of slags which are in practice. So, as we have discussed that in certain cases for the composition controls, like suppose if you want to control the amount of sulfur and phosphorus, you will have to go for basic lining process. So, basics that is basic slag has to be there. Basically it is nothing but they do not, these basic linings, they do not react with these basic slags. So, linings are done to ensure that they do not react. So, if they, the lining is basic and if the slag is basic, they will not react, but if the slag is acidic and lining is basic, they may react and they may result into other chemical compound, and that will basically spoil the life of this refractory lining. So, that is basically kept in mind. Then comes the induction furnace. So, as we know, in the induction furnace the refining cannot take place. So, it is basically for melting purpose, then churning purpose, the mixing takes place because of the eddy current motions, and the normal mixing phenomena is quite good in case of induction furnace. So, it is also from 1 kg to several tons of casting. So, that melt can be melted, that melt can be prepared using this induction furnace. In the induction furnace basically the frequency is there, you have high frequency, medium and low frequency type of induction furnaces are used. So, depending upon the frequency of the current which you use, and this it has also a monolithic type of lining structure, and this is basically very quiet operation is there. Normally the cupolas are replaced with these kind of furnaces in most of the foundries. There are many advantages of these induction furnaces, however, the disadvantage is that the cost factor and also that you cannot do the refining in this furnace. So, that is the disadvantage of these induction furnaces. Normally we go for the ferrous melting in these cases. In the case of induction furnace you have the loss of alloying elements up to quite low extent, and as we have discussed you have core type and coreless type of induction furnace. So, both types of coreless is normally used for non-ferrous materials and core type. So, coreless is used for ferrous materials and core type is used for normally non-ferrous materials, which are where the core is inserted in the metal, it is in the metal bath. So, that is how it produces the currents, eddy current. So, that is how this you have the varieties of coreless and core type of induction furnaces. Coming to the refractories for melting unit. So, why refractory is required? As we know that the main purpose of the refractory is to withstand high temperature. So, refractory basically has the quality of resistance against the temperature up to a higher value. So, they fuse, they do not fuse below 1500 degree centigrade normally, that is the minimum requirement of a refractory, that it should not fuse below 1500, because most of the melting takes place. It has to be below 1500 in non-ferrous and even for iron castings, but once we go for steel it is even higher. So, you need to have metal which should not fuse at elevated temperature, at that temperature where the melting takes place. Then it has to be chemically inert, it has to be cheap, it has to be cheap, it has to resist thermal shock, it has to resist abrasion and corrosion. So, there are many qualities which basically a refractory should have. Now, it should not react. So, basically based on that you have the types of refractories. You may have the acidic refractories, basic refractories and neutral refractories. So, the lining may be known as acidic, basic and neutral. So, in acidic basically they do not react with the acid slags. So, normally they are silica based, so that is acidic. Then you have basic, which are normally the based on dolomite or bauxite, these magnesite, these are used as the basic refractories and it has better qualities like magnesite or dolomite, they have better qualities. They have basically there are the properties, one has the superior values, but maybe at the expense of the cost. So, one may be cheaper, another may be costlier, but it may have a better property. So, depending upon what kind of requirement you have, you can use these different kinds of properties, these different kinds of refractories. And neutral, normally zirconium is used as the, so zirconium oxide is there which is used as the neutral refractories. Apart from that we have other refractories also which are neutral. So, this way you have different kinds of refractories which are used in the furnaces depending upon the requirements, depending upon the type of slags which you are likely to get, you use the different kinds of refractories. Thank you.